In 2023, Uruguay suffered its worst drought in 74 years. As this view of the Paso Severino Reservoir shows, the country's main drinking water supply ran dry, forcing authorities to mix salty estuary water into the public taps. At the height of this emergency, Google was moving forward with plans for a data center that would consume millions of liters of public water every day. This drum from the resulting protests captures the local sentiment. It's not drought, it's pillage. When you query an AI or stream a video, that action doesn't happen in a weightless cloud. It happens inside a physical warehouse packed with hardware that generates extreme levels of heat. The internet relies on the finite, highly vulnerable water resources of the local communities hosting its infrastructure, and that infrastructure is running hotter than ever. Modern AI chips generate nearly triple the thermal output of previous hardware, with some processors exceeding 700 watts. To prevent these high-density chips from physically failing under the strain of AI workloads, data center operators must pump billions of gallons of water through their cooling systems. This map shows the massive expansion of data center infrastructure and transmission lines across the United States. Much of this growth is clustered here in the desert Southwest, a region where operational and planned facilities are drawing from reservoirs that are already at historic lows. This friction is global. In Bengaluru, India, residents wait for municipal water from tanker trucks, while local data centers draw from the same strained reserves to keep their servers cool. This rising thermal demand is colliding with the reality of global water scarcity, making high-density computation an increasing risk in water-stressed regions. These industrial fans on the roof of this facility are part of a traditional evaporative cooling system, the primary method legacy data centers use to manage their temperatures. The mechanism is straightforward. Cold water enters the server racks and absorbs the heat. That water is then pushed to a cooling tower, where it evaporates into the atmosphere to dissipate that heat. Because that water is released as vapor, it is permanently removed from the local watershed. Every day, millions of liters of water leave the community ecosystem. There is also a secondary drain. The power plants required to generate the massive amounts of electricity these data centers consume need their own vast volumes of water to function. In this model, computational efficiency is bought with a community's critical drinking water. To stop this extraction, the tech industry is pivoting towards zero-water cooling technologies. These precision-machined copper and aluminum components are direct-to-chip liquid cooling plates, the hardware enabling this shift. They use a closed-loop design, where a specialized liquid or treated water absorbs heat from the processor and moves to an external heat exchanger without ever evaporating. The heat is expelled via fans, allowing the exact same volume of liquid to recirculate through the system indefinitely. The goal is to bring the metric of water usage effectiveness, or WUE, down to near zero. Other methods, like two-phase immersion cooling, submerge entire servers in a bath of non-conductive, heat-absorbing fluid to achieve the same result. Zero-water engineering moves the data center away from the legacy of resource extraction, creating a sealed thermal system. Tech companies have spent years optimizing their power usage effectiveness, PUE, to lower electricity bills. But in many towns, water has become the sharper social and operational issue. In arid environments like Phoenix, Arizona, implementing zero-water cooling is becoming a requirement for growth, allowing cities to host infrastructure without sacrificing their survival reserves. Operators that ignore this transition face increasing regulatory roadblocks and the risk of stranded assets as communities protect their local water supplies. Access to water has joined electrical power as a primary, localized constraint on how these digital networks can physically expand. To operate in the long term, tech companies must secure a social license, the unwritten community trust required to build and run these facilities. Securing that license means designing infrastructure that adds to local resilience, rather than drawing from it. Engineering choices made at the microscopic scale of a processor now dictate the health of the macroscopic environment around them. The growth of the global digital economy is now tied to the preservation of these shared local resources.